Hello students, welcome back. We went through the first two sections. Now let's do some antiderivative computations on trigonometric functions. Here's some antiderivative rules, and please remember the recurring theme of 1 over a comes from the chain rule. So the derivative of sine is cosine, so antiderivative of cosine is sine. The derivative of cosine is negative sine, so the antiderivative of sine is negative cosine. Similarly, we have tangent and cotangent function, and secant and cosecant functions. The last two are not that important, at least for the time being. In calculus 2, they're going to become important, but not just yet. The others are all important. And as for pluses and minuses, good luck. Look up the table. Here's some more trigonometric functions. And these show up several times, but these almost never show up. And then antiderivative rules for squared trigonometric functions. Oh, these are really important for calculus 2. And this is a kind of overlap between calculus 1 and calculus 2. Let's talk about this. So, okay, let's start from this. And then let's do some manipulation of sine squared. And you can use the power reduction formula. 1 minus cosine of 2x over 2. Or equivalently, 1 over 2 minus 1 over 2 cosine of 2x. And then we can apply the antiderivative rule for 1/2. Constant, so 1/2 times x. And then minus 1/2 was there before. Antiderivative of cosine is sine. And then we need extra 1 over a. And then we have plus c. Simplifying this 1/2 times 1/2, we get 1/4, and there you go. That's how you can get this. You can regard it as a formula, but most students prefer to do it with power reduction formula. You're required to do it that way in calculus 2, so maybe it's a good idea to practice it now. As for the others, they're all important in calculus 2, but I don't know if I'm going to write these kind of problems here. These two, yeah, they do show up, so do not completely disregard. Okay, so much for those, and let's go ahead with some example problems. Here we go. Antiderivative of this, well, we have a constant, trig, and an exponential. Okay, let's go ahead and do that. So how about 1? That's constant, so you're going to get just 1u. By the way, we have the u here, and the main variable is u, not x. Now cosine, antiderivative of cosine is sine. Derivative of sine is cosine, antiderivative of cosine is sine. So it's going to be sine of 3u plus 2. But you have to undo the chain rule, so you're going to need 1/3 here. Oh, by the way, this one is blue. And then let's use red for this. And then let's keep this green. So exponential always remain the same, 2u plus 1, but then again we need 1 over a. Okay, and this is going to be the green part. Satisfied? Constant times u. Cosine becomes sine, but we have 1 over a. Exponential stay the same, but we have 1 over a. The recurring theme of 1 over a. Alright, how about the next problem here? Let's put some space in between there as well. Okay, we have some multiplication here, and we cannot separate multiplication. So we had better distribute around and break out the parentheses. Let's go ahead and do that. Secant times secant, that's going to give me secant squared. And the 2 secant t times tangent of t, that's what I'm going to get. Let's put some space in between here too. Now secant squared. Any antiderivative rule associated to that? Right here. Derivative of tangent is secant squared. And then the derivative of secant is secant times tangent. So this one is tangent of t, and then this is secant of t, and then plus c. So this gave us blue, and this one green. Well, the antiderivative of secant squared is tangent. Cosecant squared is negative cotangent. Those appear quite often. This one relatively less often. Secant's tangent becomes secant. Cosecant cotangent becomes negative cotangent. Those are relatively rare. These two. Okay, all right. Now how about the next problem here? We have some fraction here, so let me expand the font. Any idea here? Well, you have one term here and 2 terms in the numerator. So let's separate the numerator. We have done this several times already. So this kind of technique should not look too strange to you by now. So separate the numerator. 3 over sine squared plus 4 sine squared v over sine squared v. Okay, so far so good. Now, do you have some simplification? Well, I hope you can see this second one really easily. Let's see, let's just color coding. Red, blue. So this is red, and that's blue, and that's blue. So far so good. So sine squared cancel out. We just have 4 constant. Now how about this? Is there any way to simplify this? 3 over sine squared. This is actually 3 times cosecant squared. Remember, cosecant is 1 over sine, secant is 1 over cosine. Now, this doesn't look too bad because cosecant squared, that's the antiderivative of, that's the derivative of negative cotangent. Derivative of cotangent is negative cosecant squared. So that's not too bad. So let's go ahead and complete it. Negative 3 cotangent of v, don't forget negative, and 4v. This is constant, so we get just 4v. And then this one, that came from the trig formula. Well, separating the numerator, typical technique you have to remember, and some trigonometry. Well, sine squared in the denominator can become cosecant squared. Nothing outrageous here. And once you have cosecant squared, well, look up the table. Sine, cosine, first two appear really often. And secant squared, cosecant squared. Not as often as sine and cosine, but they appear quite often as well, because those are related to tangent and cotangent respectively. Especially tangent. That one appears a lot. Now these two appear relatively less often, but they do. Yeah, we have a problem that requires some power reduction formula. Another one. And then, oh boy, yeah, this is gonna be something special. Let's see, enough time for maybe just one problem. Okay, let's go ahead and do this. I'm gonna leave this to you. It's a power reduction formula. We did sine squared previously, so cosine squared can be done similarly. This one is something special. I may skip, or maybe if I have time to burn, I can come back and talk about it in a separate video. For now, let's focus upon this one only. So how do you do this? Oops, sorry about that. Well, please remember Pythagorean identity. Tangent squared can be rewritten as secant squared minus 1. Remember, tangent squared plus 1 is secant squared. And then antiderivative of secant squared, oh, that's tangent. And then antiderivative of 1 is just x. So we get that, and you can regard this as a formula if you want to, but that's going to be a bit of overkilling. What's the most important formula in the trigonometry? Number 1 is by far Pythagorean identity. So you got to know those really intimately. Sine squared plus cosine squared equals 1. Tangent squared plus 1 is secant squared. And then cotangent squared plus 1 is cosecant squared. You got to know all those. Actually, you can deduce those from sine squared plus cosine squared equals 1, dividing both sides by cosine squared, or dividing both by sine squared. What am I talking about? From here, divide both by cosine squared. Sine squared divided by cosine squared. And then divided by itself, so it's 1, and then 1 over cosine squared. And what is this? Sine over cosine. So that's tangent. Plus 1 is 1 over cosine is secant. So you see, from here, you can easily deduce the other one. Dividing both sides by sine squared, you're going to get cotangent squared plus 1 equals to cosecant squared. So they're all important. Pythagorean identity. So using Pythagorean identity, associated to antiderivative rule for secant squared should not be outrageous. Difficult, yes, I understand, but nothing outrageous. As for the other problems, they're all pretty standard, so you should know all those. And as for this, okay, this one belongs a little bit better to calculus 2, but it goes like this. Power reduction formula, separate, and then apply the antiderivative rule. Okay, so much for section 3.